Hey, this is Shawn Taylor. I'm currently a postdoc at the Jornada Experimental Range in New Mexico, and I'll be talking about some of the large-scale phenology work I did for my dissertation, which I just finished last year at the University of Florida. So a large part of my dissertation work involved making this website. It hosts several hundred phenology forecasts for the timing of leaves, flowers, and fall colors for numerous species. It's been running for a while now, and it's updated 1 to 2 times every week to incorporate the latest climate data into the phenology forecasts. So the big question is, how do you get from these simple phenology observations of flowers and leaves present or absent to a large-scale phenology forecast? And the answer is, there are a ton of small steps in this process, but I'm going to lay out a few of these major themes that I learned from building a system along the way. First up is quality assurance. The first time any bit of data is touched, it should be run through some sort of data check. Even the simplest checks are worthwhile doing. For example, if you're dealing with dates, it may seem silly to check whether the correct century is used, but it's worthwhile because it can catch simple input errors which would have caused larger issues later on. And a quick shout out to the National Phenology Network, which I used a lot of their data. They have great QA methods, and among data providers, they are really at the forefront of this. All their data has flagging indicating various QA steps, and it gives you the option to choose whether something meets your needs. Along with this, they also have excellent documentation on how all these methods were derived. And a quick note, if you are utilizing your own data, there's no reason you can't do these same kinds of things yourself. My lab at the University of Florida outlined these methods to do exactly this, and the only prerequisite that it has is basic skills in R. So next up, once you're getting into actually handling data, a good coding workflow is organizing the major steps into different independent functions which pass data between each other. This makes your code, 1, very easy to read, and 2, it makes it much easier to maintain when errors pop up. So after setting those things up, your primary script would look something like this, where you first load the helper functions and then run them one at a time. After taking a break from a project and not looking at your code for 6 months, it's much easier to get reacquainted with it using a setup like this rather than a single script which can be 1,000 lines long. Also with a setup like this, it's much easier to find errors. Since they happen inside these unique functions, you know exactly where to start looking when things break. And everything will break eventually. That's just the nature of code and software. For example, I had a recent problem where the server that I get my climate forecast from was switched to a new protocol. My forecast failed for a little while, and the error that was output pointed me towards a single section of code where there was a single line that I had to change to fix it. And one step just beyond organizing into functions is making a package out of all those important steps. For example, I made this package just for the modeling aspect. This again makes your code easier to maintain, and it's easier for other researchers to use in their own work. And an important part of the forecast system is you can always view the latest forecast on the website. That's because it lives on a server in the cloud that isn't connected to anything I've talked about so far. All this modeling stuff happens behind the scenes and only updates the website when things run successfully. That way, when NOAA changed their servers and broke my stuff, the forecast site was still always available, regardless. And the code organization I discussed also has the benefit of being able to pick the best available software tool to do each step. For example, a lot of the data processing work is done in R, while the phenology and climate modeling stuff is done in Python. Each of these have their own strengths and weaknesses, but they can be used together seamlessly by passing data between them in these common data formats. For example, we all use CSVs, and CSVs can be used interchangeably between any common programming language today. So in the end, if you're dealing with big data in phenology, there are a ton of tiny steps you have to do. But if you stick with these basic principles, you're going to have code that is much more reproducible, easier to share, and much easier to maintain in the long run. Thank you.